Hi everyone. In today's lesson, we're going to talk about another concept of an application to derivatives, and it's called related rates. So these are real-world applications to implicit differentiation. So the best way I can do it is just by looking at the first example. So let's read it together. Example number 1. The top of a ladder is sliding down a wall at a rate of 3 feet per second. And they want to know how fast is the bottom of the ladder sliding along the ground when the top is 6 feet from the ground. So the first thing you want to do is draw a picture. So I put a building or a little house here to show you where the building is. And we've got a 10-foot ladder sliding down the wall. So I'm going to draw my ladder. So I just like to say, here's my ladder right on top of the building. And here it is. And this ladder is sliding down the wall. So it's not sturdy enough, so it's just sliding. So you kind of have to use a little bit of imagination to see that it's going down, but that's kind of the concept. You really can't draw the motion of it. But it's sliding down at a rate of 3 feet per second. And they want to know how fast is the bottom of the ladder going to slide. So obviously, as this comes down, this bottom part's going to kick out. So as this one slides down, this one slides that way. So the idea is that this ladder here is going to go down when this kicks out this way. So what you can kind of see here is that you're making a right triangle with relationship to the wall. So from here to here kind of creates this right angle. And the 10-foot ladder, that distance is never going to change. So we can label the hypotenuse with 10. And I could label this horizontal distance as x, and I could label this vertical distance as y. So now let's continue to read the rest of the question to see if we can substitute some variables. So we have that the top of the ladder is 10, so that's here. But now they give us this piece of information that the ladder is sliding down the wall at a rate of 3 feet per second. So we're talking about this distance here changing over time, right? The ladder goes down with respect to time. On average, it goes 3 feet every second. So 1 second it goes down 3 feet, then another second it goes down 6 feet, and so on and so on. So when we talk about an average rate, rate is considered change in y over change in x, therefore slope. And in calculus, we think of slope as derivative. So our dy, derivative of the y distance, this distance, over time, so instead of dx like we're used to, derivative, we call it dt. So the change in the y distance over time is 3 because the y value, the ladder's distance, is going down on an average of 3 feet. So when you write the derivative, also make sure that you put -3. So the key word here, rate, is always going to be the derivative. Rate is derivative. Derivative means slope. Okay? So we have the dy dt, the change in y's distance over time. If you want to write that, you can. So change in y distance over time is -3. And they want to know how fast, so what is the rate, how fast is the bottom of the ladder sliding along the ground, so when this kicks out. So they want us to know, they want to know what is dx over dt. How is the x value changing over time? When, specifically, when the top of the ladder is 6 feet from the ground. So they're saying we've stopped it at a specific point, and this y value now is 6. The top of the ladder is now 6 feet from the ground. What would this change be? So how can we figure this out? Well, we're going to use a little bit of implicit differentiation. And we know that a right triangle, to find the lengths of the sides of a right triangle, we can use the Pythagorean theorem. So a squared plus b squared equals c squared. But in this case, I'm going to use x and y. So we'll make this x squared plus y squared equals, we'll call this z squared. I'm just calling the hypotenuse z. So x squared plus y squared equals z squared. And we're going to take the derivative because the only way I can find change in time or a rate, change in time or change in distance over time, I need to take the derivative. So what's the derivative of x squared? You should be saying 2x. But because we're talking about time, we have to do this implicitly. So what this means is we're taking the derivative of x with respect to time. So every time we take a derivative, we have to put its rate next to it. Then the next one, what's the derivative of y squared? You should be saying 2y. And the derivative of y with respect to time. And then the last one is what's the derivative of 2z? So that z squared will be 2z, but I took the derivative of z with respect to time. So I have these dx dt, dy dt, and dz dt. So let's plug in what we know. In our picture, we don't know x, but we know y and we know z. The hypotenuse will be z. So maybe what we could do first before we plug into this formula is actually find this x. So I'm going to do a quick Pythagorean theorem over here. Leg squared plus leg squared equals hypotenuse squared. 6 squared is 36. 10 squared is 100. I'll subtract 36 on both sides and get 64. Take the square root, that gives me 8. So this x value is 8. So what I'm going to do now is, since x is 8, I'm going to put that in here. Since y is 6, I'm going to put that in here. And then since z is 10, I'm going to put that in there. So 2 times 8. Now dx dt is actually what we want to solve for. So notice that's what we found out over here. So we're going to leave that as dx dt and we're going to solve for it. Then we have 2. Y is the 6. And dy dt is actually negative 3. And z is 10. That's the distance of the hypotenuse. So 2 times 10. And then this one's interesting, dz dt. If dy dt is the change in the y distance over time, then dz dt will be the change in the z distance over time. But does the latter ever change distance? No, the latter is always staying the same size. So the dz dt is actually 0 because I'm never changing the distance of this ladder. I'm not extending it or making it smaller. The ladder is just 10 feet. So that dz dt will be 0. So we have now 16 times dx dt. And then we have 2 times 6 is 12. 12 times negative 3 is negative 36. So minus 36 equals 0. And then we can solve for dx dt by simply adding 36 on both sides. So 16 times dx dt equals 36, and then divide both sides by 16. Dx dt equals 36 over 16. So the question should specify what to round to, but it doesn't. So why don't we just round this to the nearest hundredth and get our final answer? So why don't you type that into the calculator and then hit resume when you're ready for the answer. Okay, so you should have gotten 2.25. So 2.25 is our change in distance, this x distance, over time. So since our rate is expressed in feet per second, make sure you're doing the same thing with this answer, feet per second. Now, the last thing that you want to make sure that you do is check to see if your answer makes sense. So notice your rate, the distance of x over time, is a positive 2.25. Does that make sense in context to the problem? Should it be positive? Well, if this ladder is kicking down and this is kicking out, aren't I extending this x distance? And if I am, then my rate should be positive because I'm increasing. So what this 2.25 means is that this ladder is going to kick out on average 2.25 feet for every second that this is dropping. So this is going to be extended longer. All right, that's it for the first example. Let's try example number 2. All right, so same scenario. We have a 25-foot ladder this time. So I'm going to draw my picture as I read. So here's my ladder leaning up against the wall, 25 feet. And this time they're saying that the base of the ladder is being pulled away. So you have somebody here pulling this ladder this way. Therefore, the top of this is going to come down. So this distance is going this way, while this distance is going down. So similarly as before, we still create that right triangle. So because the information that they give you now is different, they're saying the base of the ladder is being pulled away from the wall at a rate of 2 feet per second. So this distance is being pulled that way. So we're extending this distance, so the rate should be positive. But this time it's the x. So dx dt is a positive 2 feet per second. So this is your change in x distance over time. And again, it's positive because I'm gaining more distance. I'm making it bigger here. So we'll call this x like we did before, and we'll call the vertical distance y. So they want to know, how fast is the top of the ladder moving down the wall? So how fast is this distance changing? So that's dy over dt. That's your question mark. They want to know, when is that happening? When the base of the ladder, bottom of the ladder, is 15 feet from the house. So they're telling you now that this x is going to be 15. So notice they're giving you different information. So can we calculate the y? Because we know we're going to need that from before. So another Pythagorean theorem here. So 15 squared plus y squared equals 25 squared. 15 squared is 225. 25 squared is 625. And subtract 225 on both sides. And we get y squared equals 400. And we take the square root of both sides. And we get 20. So this y distance is 20. Okay, so we start the same way as we did before. We have the Pythagorean theorem, x squared plus y squared equals z squared. We're going to take the derivative of each of the parts. So 2x, but now dx over dt, plus 2y times dy over dt equals 2z times dz dt. So these first steps are going to be the same. You're going to take the derivative. You're going to need the Pythagorean theorem to find the missing side. So now x is 15, y is 20, and z is 25. So I can go ahead and plug those values in. So x is 15. dx dt we actually have, which is 2. I got that from here. The y value is 20. We just found that. dy dt is what they want to solve for. The distance z of the ladder is 25, and dz dt is 0. And this is always going to be 0. dz dt will always be 0. Why? The distance of the ladder will never change. The change in x distance over time, that will change, right? This is your x value. That'll change. This will change. But the actual distance of this ladder will never change. So now we can go ahead and simplify what we have. 2 times 15 is 30. 30 times 2 is 60. Plus 40 times dy over dt. 25 times 2 times 0 is just 0. And we'll subtract 60 on both sides. And we get 40 times dy over dt equals negative 60. Divide both sides by 40 to get dy dt by itself. So go ahead, pause the video, and then hit resume when you're ready for the answer. Okay, so you should have gotten negative 1.5 as your final answer. But notice we have to put the rate in. It's feet per second. So make sure you're writing it as negative 1.5 feet per second. And does that make sense? Does the negative make sense? We're trying to find dy dt, this distance over time. So since this ladder is moving down, it makes sense that it's negative, right? As this bottom kicks out, this ladder is going to move down. So you definitely should have gotten a negative. All right, that's it for today. If you have any questions, now's a good time to jot them down and then ask us in class tomorrow. Okay, have a good night.